Well, that's a fundamental question which challenges everything we know about physics, because we know of no phenomenon in nature where, say, things come in and then nothing comes out, or you begin with nothing and then something occurs.
Then we may be entering a new era in physics. An era where there are weird features of the universe that we cannot explain. An era where we have hints that we live in a multiverse that lies frustratingly forever beyond our reach. An era where we will never be able to answer the question, why is there something rather than nothing? Thank you.
When you think about nothing, you have to be a little more careful than you normally are, because in fact nothing is a physical concept, because it's the absence of something, and something is a physical concept. And what we've learned over the last 100 years is that nothing is much more complicated than we would have imagined otherwise. For example, the simplest kind of nothing is the kind of nothing of the Bible, say an infinite empty space, an infinite dark void of the Bible. You know, nothing in it, no particles, no radiation, nothing. Well, that kind of nothing turns out to be full of stuff in a way, or at least much more complicated than you might have imagined, because due to the laws of quantum mechanics and relativity, we now know that empty space is a boiling, bubbling glue of virtual particles that are popping in and out of existence at every moment. And in fact, for that kind of nothing, if you wait long enough, you're guaranteed by the laws of quantum mechanics to produce something. So the difference between empty space with stuff in it and empty space with nothing in it is not that great anymore. In fact, they're different versions of the same thing. So the transition from nothing to something is not so surprising. Now you might say, well, that's not good enough because you have space. Where did the space come from? Well, a more demanding definition of nothing is no space. But in fact, once you apply the laws of quantum mechanics to gravity itself, then space itself becomes a quantum mechanical variable and fluctuates in and out of existence. And you can literally, by the laws of quantum mechanics, create spaces and times where there was no space and time before. So now you've got no particles, no radiation, no space, no time. That sounds like nothing. But then you might say, well, you know what? You got the laws of physics. You got the laws of nature. The laws themselves are somehow something, although I would argue, in fact, that is not at all obvious or clear or necessary. But even there, it turns out physics potentially has an answer. Because we now have good reason to believe that even the laws of physics themselves are kind of arbitrary. There may be an infinite number of universes, and in each universe that's being created, the laws of physics are different. It's completely random. And the laws themselves come into existence when the universe comes into existence. So there's no pre-existing fundamental law. Anything that can happen does happen. And therefore you got no laws, no space, no time, no particles, no radiation. That's a pretty good definition of nothing.
When all of space was at a point, that's the Big Bang singularity, how did that make sense? And there are possibilities, there are mathematical possibilities. One of the ideas I'm exploring right now is the idea that just as there is no absolute time in physics, and we learn this in relativity, that different people will literally measure different time on their clocks, and there's no absolute space, different people will likewise see different versions of space. So maybe there's no absolute scale in physics. You know, we're all used to 1 meter or 1 kilogram units. And a very natural idea is that there are no fundamental units in physics. These are units which are a result of what we call symmetry breaking. There's a symmetry under scales, which actually Maxwell's theory has. That's why it has X-rays and radio waves and light waves, and they're all basically copies of the same thing on different scales. So that kind of scale symmetry can be brought into physics. And that's a very natural thing to use to explain how it is that space could be at a point and yet still describable. Because if scale doesn't matter, then the fact that the space is shrunk down infinitely far doesn't matter either, and our equations can still be perfectly valid. So I'm trying to give a glimpse of mathematical approaches to handling this problem, which I believe are very promising in sort of mathematical theory, but also experimental.
We can see some plausible steps. We don't know all the answers, and I don't claim we know all the answers, but even the fact that the laws of nature themselves could have created everything we see, all 100 billion galaxies, each containing 100 billion stars, from nothing is absolutely remarkable.
What came before the Big Bang?
The philosophers in ancient times used to say, how could something arise from nothing? And what's amazing to me is that the laws of physics allow that to happen. And it means that our whole universe, everything we see, everything that matters to us today, could have arisen out of precisely nothing.
The fact that empty space has energy is that instead that expansion is speeding up, getting faster and faster. It's changed everything, in particular, our view of the future. Science has made it possible that the universe didn't need God, that God is redundant. That's a dramatic concept. Now, science doesn't require there not to be a God, but as Steve Weinberg said, it makes it possible to have a universe without one. And that's a central possibility, which makes our current understanding of the universe totally different than it's been for the last 2,000 years. One of the most amazing realizations of the 20th century was that quantum mechanics, combined with relativity, allows something to come from nothing. In fact, nothing is unstable. Religion and theology, and to some extent philosophy, have contributed almost to nothing to our fundamental understanding of the universe. Because questions such as what is something and what is nothing are really scientific questions, not philosophical ones. When we apply quantum mechanics to gravity, the truly remarkable thing is that even space itself can be created from nothing by quantum mechanical effects. There's been a revolution in cosmology in the last 25 years. We now understand that the dominant energy in the universe resides in empty space, and that's changed everything. And in fact, it helps point unambiguously to the possibility that the universe arose from nothing. It turns out the universe we live in is perhaps the worst of all possible universes for the long-term future of life. In the far future, the universe will become cold, dark, and empty, and life will end. Nothing will once again reign supreme. Science has changed everything about the way we think about space and time. And in fact, it's told us that empty space is in fact not empty at all, but a quite complicated boiling brew of virtual particles. It's changed our picture of nothing and also of something. These questions are not the same as they were 2,000 years ago. Given our current understanding, it could be that even the laws of physics themselves are not immutable. They could have arisen spontaneously and be different in different universes. In that sense, even the laws of physics could be an accident. The far future of the universe will be very different than it is now. All evidence of the Big Bang expansion will disappear. All the galaxies we now see will be gone, and we will appear to live alone in a cold, dark, empty universe. Everything we see is just a 1% bit of cosmic pollution in a universe dominated by dark matter and dark energy. You can get rid of all the things in the night sky, the stars, the galaxies, the planets, everything, and the universe will be largely the same. Every atom in our body came from stars. In fact, the atoms in your left hand may have come from a different star than the atoms in your right hand. The elements that were created in the Big Bang were just hydrogen, helium, and lithium. But the important elements for our existence, carbon, nitrogen, and oxygen, all of those things were created in the cores of stars. And the only way they got into your body is if those stars were kind enough to explode. So forget Jesus. The stars died so you'd be born. Quantum mechanics combined with relativity tells us that empty space can actually contain energy. In fact, the empty space and the protons inside your body are exactly where most of the mass of your body comes from. When we do the same calculations to try and understand how much energy there is in empty space outside your body, truly in space, we come up with an answer which is off by 120 orders of magnitude. It's the biggest mystery in science to try and understand where the energy we see in the universe comes from. We used to think, sensibly, that gravity was always attractive, and therefore the observed expansion of the universe should slow down over time. But what we've discovered with the fact that empty space has energy...
If you add together sort of the three kinds of things that occupy the universe. The familiar matter, that's what we're made of and what our telescopes detect. The dark matter, that's the source of 85% of all the gravity we see in the universe, and we don't know what's causing it. And the dark energy, the stuff that's making us accelerate against the wishes of gravity. Each one of those components creates a curvature of the fabric of space and time, just as prescribed by Einstein's general theory of relativity. If you add those curvatures together, what you find is that they create a universe that is perfectly flat. Flat. Now, that's not the only shape the universe could have had. The universe could have negative curvature, and if it did, that would have a saddle shape. And a negatively curved universe has a net positive energy. The universe is neither a spherical shape, the shape of a ball. That would be positive curvature, having net negative energy. Now, another way to get insight into this is to think about the energy of orbits. An object in orbit is gravitationally bound to what it circles. And bound orbits have negative gravitational energy. That's how we describe this system. Increase the elongation of the orbit by pumping energy, giving more speed to the object, and the circle distorts and becomes an ellipse. Give it even more speed, the ellipse gets more and more elongated. There's just the right amount of energy, just the right amount of extra speed you can give this object so that it goes so far away it never circles back. In fact, it escapes to infinity. At that point, that object and the system and the orbiting object and the object around which it formerly turned has zero total gravitational energy. And that path is formally called a parabola. Give the object even more energy, then it gets to infinity and keeps going. That has net positive energy, and we call that trajectory a hyperbola. Now, you've actually seen these shapes before at home. Take a flashlight. All flashlights have a cone of light that emerges from them. If you take it and aim it straight at a wall, it'll make a perfect circle. Take it and tip the angle just a bit. That circle distorts and you get an ellipse. Tip the flashlight so it's parallel to the wall, and you'll see the shape on the wall and it'll take the form of a parabola. Angle it a little more, it opens up even further and you get a hyperbola. Try that at home. So, these are what we call conic sections, intersections of a cone of light. And they relate to orbits and they relate to the energy that those objects have. Now, if your space-time is flat, just as if your orbit were a parabola, it means the universe, the entire universe, possesses zero net total energy. Think about that. If the shape of the universe were anything else, positively curved or negatively curved, it would not have zero energy. It would have negative energy or positive energy. We have zero net total energy. Now you wonder, is that good or bad? There's a silver lining to this. What it means is that you can create the entire universe out of nothing because nothing has no net energy associated with it. Had the universe been endowed with either negative or positive energy, we'd be forced to confront the questions of what was the original source of energy that begat the universe? And if it had some amount of energy, why is it that amount and not some other amount? The fact that we live in a zero energy universe bypasses that line of questioning. And does it leave us content in our emptiness? Perhaps. But we're no less enlightened by the ignorance that led to it.